So this is class 12 of our research and grantsmanship classes. Today we'll be talking about data analysis in case control studies. Our teacher for today is a treasured member of the Faculty of Clinical Sciences. She's a senior lecturer in the Department of Community Medicine and Primary Health Care. Dr. Bisola Adebayo, a very warm welcome. Please tell us all we need to know about case control studies.
Good evening, sirs and ma'ams, all protocols duly observed. My name is Bisola Adebayo, a lecturer 1 in the Department of Community Health and Primary Health Care. I apologize, I'm still on the road, so there might be some interference. So today we'll be talking about data analysis in case control studies. Case control studies are an important epidemiological design. When we look at the hierarchy of study designs, it's a bit, intermediate. It's rated higher than cross-sectional studies, but lower than cohort studies and, of course, experimental studies. But hopefully by the time we're through the lecture, we'll understand the importance for it. So the objectives of the session, at the end of this session, we should be able to describe how we build up a case control study, identify the steps. We are going to talk about issues in the design of case control studies, strengths and weaknesses, and then we're going to discuss the analysis of unmatched and matched case control studies. So this is the outline. We'll look at an overview because I didn't just want us to jump into the analysis without understanding the concept of the case control study. So we'll do an overview, then we'll talk about measures of association in case control studies, and then we'll look at how we test for statistical significance, and then we'll talk about matched case control studies, and we'll also mention confounding slightly. So a case control study is an observational study, and it's observational because the researcher does not manipulate any variables. We're just recording what we see happen as it happens. However, it's an analytical study because we try to draw inference. So when we look at epidemiological study designs, we remember we have the what, who, when, and why, and how. Cross-sectional studies speak to the what, the who, the when. But when we now talk about analytical studies, we're talking about the why and the how, which is trying to look at determinants for health outcomes or for effects in a study that we're studying. Now, generally, we associate case control studies with being retrospective. And the key thing about it being retrospective is that at the time we're commencing our study, the outcome is already known, and we're working backward to determine exposures. So it's retrospective by the definition of the point of view of the outcome being known. So case control studies proceed from the outcome or the effect to the cause or the exposure. And we select participants for the study based on the status of their outcome. Then data on exposure is collected retrospectively. By definition, it's an observational study in which subjects are entered into the study relative to the presence, that's a case, or absence of the outcome or the effect. The two groups are then compared as to their exposure to the suspect causal factor. So the important difference is that in a case control study, you have two mutually exclusive groups. You have cases and you select controls. They are mutually exclusive. However, the converse in the cohort study, in which we generally tend to follow up people, even when it's retrospective, we're still following up from exposure to outcome, is that they're out of the same pool, unlike a case control study. So the first thing is that we select our cases and our controls, and then we measure our outcome. So this is how it works. So we have cases, and within our body of cases, we have people that are exposed and those who are unexposed. An example here is lung cancer, and we're looking at example of exposures that might find is whether or not they smoke. And then we now break the cases down and now look at the exposure exposure, those that are exposed to smoking or those that are not exposed to smoking. And we do exactly the same thing for the controls. We have controls, and the only difference between cases and controls is that the controls do not have the outcome or the effect. That they don't have lung cancer. But some of them smoke, some do not. So we also now break them down into those that smoke and then those that do not smoke. Now, when do we conduct a case control study? It's an excellent study when the outcome of interest is rare, when we have very rare diseases like some cancers. We know we're looking for cases that are available. So we don't have to wait for people to develop it. So we can go retrospectively, look at registers, look at registries, and then try and find out cases that exist. And then we now select our controls. And then the other thing is that we're already working from the outcome. We can find multiple exposures. And then it's useful when time is limited, like experimental or cohort studies that you're forging ahead. Those ones can take a bit of time. And then funding as well, because many times you're working retrospectively. So a lot of your data is there. And usually a case control study can be a good study to conduct before you now do a cohort study or an experimental study. It's also an important study when, an experimental study. It's important when experimental trials are not ethical or feasible. And then it can also be used when you cannot do a cohort study. So before we move ahead, let's briefly look at the advantages and disadvantages of cohort study. So we've already said that it's cost effective relative to other analytical studies. So we don't have a long period of follow-up. It's effective for rare diseases. You can study multiple exposures. You usually need fewer study subjects. So what you can do is increase the ratio of your cases, your controls to your cases to make up the study size and ensure that your study is well powered. However, one of the disadvantages, it cannot calculate incidence because incidence is a measure of risk. I remember we're comparing two mutually exclusive groups and we already have the outcome has happened. However, in a cohort study, at the point where a study commences, people have not yet developed the outcome of interest. Then case control studies can also be prone to bias, particularly selection bias. Sometimes you have to be careful that you don't misclassify. You don't misclassify your cases and your controls. And then because you tend to work with retrospectively, people may recall differently. Many times, those that suffer the ailment or the effect may remember differently from those that didn't. They will try and look for what are the possible causes themselves. Did I eat this? Did I do that? However, a control is just living his life. So you may have differential responses from them. And then you might also have observer bias. So people rely on their memory, and then people with a condition are usually more motivated to recall risk factors. Then one important challenge with a case control study is that it might be difficult to find the appropriate control group. And then it's not useful for rare exposures because it will take a long time before you have enough to study. And you can only examine one outcome. So this is the basic design of a case control study. We have our study population, and then we have a subset of the target population randomly selected. And you need to define your inclusion and exclusion criteria by which you classify people. So we select our study participants just like any other study with our inclusion and exclusion criteria. And then we then select our cases and controls based on health outcome or disease status. So we have our case group and our control group, and then we look back in time, and then we assess both groups. So a typical example, we did a study on tuberculosis, and we used cases. We used incident cases, people that were newly diagnosed with tuberculosis in Lagos State. So we selected our cases from dot clinic across the state after doing, sampling. We did a multi-state sampling. We divided them and we selected from each of the senatorial districts. So with a case control study, many times it's easier to first select your cases After you select your cases, then you can now go ahead and then select your controls. And as we'll see as we go on, your controls should be as similar to the cases as possible. As much as possible, they should also be people that will be at the same risk. The only difference is that they do not have the outcome of interest. Case control studies, for example, are commonly done for outbreaks. Like this cholera outbreak, you find out all over Africa. That if you look online, you see that it's something they commonly do to try and identify, to try and identify exposures, because you don't know everybody. So, for example, in Lagos some years ago, had a cholera outbreak around Oshodi Solo. That was around one of the communities, around Ago. So if our cases are in Ago, Oshodi Solo is large, even though it's the same local government. It won't be appropriate to come and select our controls from somewhere very far in Oshodi and say just because it's Oshodi, maybe we go to Bolade. As much as possible, there should be people from the same locality, have similar kinds of exposures, lifestyle, but they do not have the outcome of interest. So this is the general sequence. When we're preparing for a case control study, we have to define or prevalent cases. Then we select our controls. We decide if we want to match. Then we do our data analysis. So the measure of association we directly calculate is the odds ratio. But if you want to test whether that odds ratio is significant, we can then do a chi-square, and you can also do a logistic regression, and then we interpret our results. So now when we look at our steps, like what we said before, we define our source population, we determine our cases. So you have to decide what are the criteria by which you define somebody as a case. We determine our controls, then we decide on the ratio of cases to controls. Minimum, we should have 1:1. Controls ideally should not be less than, the number of controls should not be less than the number of cases. However, beyond 4 controls to 1 case, there's little added value in terms of statistical efficiency. Then we decide if we want to match our cases and our controls. And we estimate our sample size, we select them, and then we measure our exposures, we analyze our data. Going back to our study on TB, so we're looking at quality of life of patients with tuberculosis. And initially, we're just thinking, it's just going to be a regular prevalence study. And I remember Professor Hussein asked a question, and he was like, how do you know that the quality of life is from TB and not from the stress of living in Lagos? Which is very true. And so we realized that we needed controls. So that's how we now went to select controls within those same communities. And we now had to match, the controls to the cases. And it's a very tedious process, because for every single case you have, you will look many times. The key thing many times is to match, for age and sex, because those are common confounders in studies. Some other things we did stratification, which I will explain later. So for each age group, for each age group, you have to select somebody, similar gender, similar, if you use 5 or 10 year brackets. So like that, for every case, you have to select the appropriate controls. Then we estimate our sample size. We'll briefly just see it here, which we can have in the slide. And then we select our cases and control, measure exposure, and analyze our data. So the issues to consider when designing our case control study, you have to clearly define your hypothesis. So like any other study that we're doing, ideally you should start with formulation of a clearly defined hypothesis. Then we have to define who we mean by our case. We have to do this at the beginning, and it's not something that can shift along the way. So we have to clearly define our case at the outset to make sure that all the cases that are included in the study are based on the same diagnostic criteria. And then we have to determine the source of our cases. So now let's go to cases, and then we talk about controls. So first, cases should be homogeneous. So we have to use the same definition for them. You decide, are we using incident or prevalent cases? Incident cases are people that are newly diagnosed cases. Prevalent is those that may have had the disease for some time. So you have to, even in prevalent, you need to define your time frame. And then you set inclusion and exclusion criteria, on the different variables depending on your study. And we should know that if cases are misclassified, then the association we have may be false. Now, our cases can be sourced from various places, and many times it's common to use cases from facilities because that's the easiest place, that's where diagnosis is made. So many times that's the easiest place to get our cases. So we might recruit them from a number of sources: health facility, clinic registers, population bases, even a lab, even lab registers. And then we also decide, are we using patients on admission, discharge patients, outpatients, because all these things may have implication. Now, cases can also be population-based. People can select cases based on death certificate, disease registries, incident cases in an ongoing study. Sometimes people might be doing an ongoing cohort study, see something important, and choose cases and do what they call a nested case control. So you select some cases and controls in that study that don't have the outcome of interest and do a case control that is nested within a cohort study. Sometimes you might also select your cases from cases that are reported by the surveillance system. Now, with regards to controls, the ideal controls are healthy controls. And sometimes there's a question, what's really healthy? How well can you determine that? Conceptually, control should also come from the same population at risk from which cases may develop because you want them to be similar kinds of people. But practically, they're often selected to be similar on key factors, but without the disease. Because sometimes you might not be able to determine who exactly is at risk, but we try and make them as similar as possible to the cases, except for the disease. You can have different types, and the aim of selecting controls is to so why do we have controls? To compare exposure rates among cases and controls and confirm or refute that the fact that the risk factor has occurred more frequently in cases of control using the measure of association. So what are type of controls? We have population controls, hospital controls. They may be convenient, however, may be affected by characteristics of the disease that brought them to the hospital, even though it's not interest. We also have neighborhood controls and death controls as well. So these are just the advantages and disadvantages of two that generally hospital controls are more accessible. Patients have time to participate. But differential hospitalization patterns may introduce some bias. And community controls tend to reduce selection bias, but it's more time intensive, it's more money consuming. You may have lower participation rate. Those in the hospital tend to not to be averse because you have the undue advantage. You might be treating them and they might be better what they call it, they better cooperate with the researcher. Sometimes you have multiple control groups because of some limitations. So some people in some studies, they could use living and death controls. You could use hospital and community controls. If findings are in agreement between groups, then they are likely to be valid. For example, in a cholera outbreak, this cholera outbreak, I know that they're doing a case control study and you find out they're using both neighborhood control and work from the area where people work because most people in Lagos tend to spend more time at work. A lot of the activities take place. They may have minimal exposures even where they are. So a summary of all this that we've talked about with regards to the controls and the cases. At the baseline, we select our cases and control based on health outcome or disease status. At the point where we are starting, the exposure status is unknown. After cases and controls have been identified, the investigator then determines the proportion of the cases and the proportion of the controls that have been exposed. So now we'll be mentioning the word exposure. So now let's talk a little about measuring exposures. So exposure is measured to assess the presence or level of exposure for each individual for the period of time prior to the onset of disease or condition under investigation. when the exposure would have acted as a causal factor. Sorry for that typo. Case control studies is difficult to establish temporality. That is, which started first, the exposure or the outcome, because we measure exposures out after outcome has already occurred. So it's subject to both recall and observer bias. And the procedure for collection data should be the same for the cases and the controls. So there are various methods we can use in research. We can use standardized questionnaires, depending on what we're interested in: biological samples, interviews, medical records, employment records, pharmacy records. It varies depending on the study. And then when we are analyzing case control, so now we're coming to the meat of the matter, we usually use the odds ratio. The odds is a measure of association between mutually exclusive events. So we usually use the odds ratio to estimate the strength of association between exposure and outcome. And we must say it again, you cannot use case control to determine incidence, because incidence is a measure of risk. And at the point where you are starting from, the outcome has not yet occurred. And we usually present our case control study in simplest form in a 2x2 table. So it's also called a contingency table. And we usually have the cases, the controls, then we have the exposed and the unexposed. So this is how it looks. So the odd ratio is a measure. We're looking at the ratio of odds of exposure among the cases to odds of exposure among the controls. So you have two groups. You have cases and you have controls. And you're looking at what are the odds of the controls having the exposure. You're also looking at what are the odds of the cases having the exposure. Now let's delve into odds. So this is how a complete table will look like. So the main thing is to first understand the contingency table. So first of all, we have cases, and you can see that's the column. So in this table, we have cases that are both exposed and not exposed. So the total number of cases we have are A plus C. Then we have our second group, which is controls. Some are exposed, some are not. The total number of controls, we have B plus D. And the grand total is A plus B plus C plus D. Now, when we look at the rows, we have exposed and unexposed. The total number of people that are exposed are A plus B, while unexposed is C plus D. But remember, in this, we are comparing two groups, cases and controls. Oh, sorry, sorry, I think my thing was jumbled up. Sorry, I have to move. I'll come back to that. Okay. All right. So now, when we say odds, the odds are the probability that the cases have an exposure over the probability that the cases don't. That's the odds for the cases now. So first, we're looking at cases. Before we go to odds ratios, we want to look at the odds themselves. So the odds are the probability that the cases have an exposure over the probability that the cases do not have exposure. So first of all, what is the probability of an exposure in the cases? Let's go back to that table. If we look at this table, remember we said the total number of cases is A plus C, and the total number of cases that have the exposure are A. So the probability of probability of exposure is A over A plus C. And the probability of non-exposure is C all over A plus C. I hope we're all getting this. I want to break it down. So, everybody knows odds ratio is AD over BC, but many times, it can be confusing. But if we know how we arrive at it, then it's easy to always recall. So we have cases, total number, A plus C, exposed A, unexposed C. So the probability of exposure in them is A over A plus C, and probability of non-exposure is C over A plus C. sorry, in the rush. I think so that's what we have. So remember that we said probability, odds are probability that they have an exposure over probability that they don't have exposure. So there are two mutually exclusive events. So if we do that, this is what we get. That's how we get the A over C. So it's A all over A plus C. That's probability that they have the exposure, all over C all over A plus C, which is probability that they don't have exposure. Remember, it's the same group, they are cases, total number A plus C. And so when we work it out, the math, it comes down to A all over C. We apply the same thing to the controls. And this is probability of exposure among the controls and probability of non-exposure. So remember that for the controls, we have the total number is B plus D. Exposed, total number of those exposed is B, total number of those unexposed is D. So one thing about the case control studies is we see that dichotomous is you have or you don't have. So generally there's no in between. You know, in the classic case control, it's either the person has the exposure or it doesn't have. The other person is a case or is not a case. So it's like flipping, you know, heads and tails. There's no in between. So that's the odds. So when we calculate it the same way as well, we get D all over D because the denominators cancel out. So if we now look at the odds of exposure in the cases, because remember it's cases that we're interested in, that's why they're on the top. And compared to the odds of exposure in the controls, when we now get, remember, it's now A over C or B over D. By the time we do the cross multiplication, that's how we arrive at the AD all over the DC. The beauty of it is that all our statistical packages can do this for us. So this is just to understand. And how do we interpret the odds ratio? If we get an odds ratio of 1, the odds of the disease is the same for the exposed and the unexposed. If we get an odds ratio of greater than 1, exposure increases the odds of the disease. Less than 1 reduces the odds of the disease. So now, you know, we calculate our odds ratio. Then what do we do with it? How can what inference can we make from it? We now have to subject it to statistical test. So easily you run your chi-square 2x2 analysis. So I didn't bother bringing that in because at this stage, I know that we're all researchers, and usually when you even run your data in SPSS or R or EpiInfo, you can do the chi-square 2x2 analysis. So that already tells us. So chi-square, we use it for categorical data. So we can do our chi-square, and you can also do your Mantel-Haenszel statistics. It's all in the data. So it takes account variations in substrate strata will come down to that data. An example, let me give, for example, I'm working on TB, and I say that okay, patients with TB have poor quality of life, controls have good quality of life, but in between them may be variables and may be confounders. For TB is for example, is a disease of poverty. So I have to look, does socioeconomic status have an effect? So what you usually do with Mantel-Haenszel statistics, I now do substrata. So I now compare, I break down my TB cases into those that are maybe high and low, and the same thing for the controls. I now compare to see if there are differences. We'll look at it later. So I can see if socioeconomic strata affects both of them or has an independent effect on the quality of life. So that's just how it goes. And then you also have the Fisher's exact test. And then for multivariable analysis, you can do unconditional logistic regression. We don't need to go into the nitty-gritty of that. Can run it in our software, and it will tell us, because the good thing about the logistic regression is that in your model, you put in your key variables, particularly you can put in those that have been significant. You define the level of significance for the logistic regression, and you put them in your model and see whether it has an impact on your original hypothesis. So just to do an example, For example, if we look at osteoarthritis as an outcome, and we say some have, some don't have, and we look at being defined as obese as having an association with it. If we have this kind of table, we have this type of table. We have cases that deal with osteoarthritis. We have a total of 72. Those are exposed, as those are obese. They're 50 out of the 72, unexposed 22 out of the 72. For the controls, we have a total of 178. The exposed are 73. That's those that are obese, while unexposed, those are not obese, are 105. And then you have a total of 250. So it's going to go the same way. So if we break it down step by step, probability of those obese being, of those with osteoarthritis being obese is 50 over 72. While probability of those with osteoarthritis not being obese is 22 over 72. So the odds of being obese among those with osteoarthritis is 50 over 22. We do the same thing for the controls. Let me refer back to the table. So you see we have exposed 73, unexposed we have 105, and then total we have 178. So the probability of the controls being obese is 73 over 178. The probability of the controls not being exposed, not being obese is 105 over 178. So if we want to find the odds that those without osteoarthritis will be obese, you now divide those two figures by. So this is what we have. The odds are 73 over 105. And then this is the odds ratio. We find out that they have 3 times. So that's how we define it. So the odds are 3 times in those that have osteoarthritis compared to those that do not have osteoarthritis. That's all of them having exposure. Now we mentioned sample size. This is a sample size calculator for the case control study. N is our sample size, R is the ratio of controls to cases, then variability, define, we have our P and 1 minus P, then we have our desired power. So that P, is prevalence, and then 1 minus P, and then we have our effect size, which is difference in proportion, and our desired level of significance, which is 0.05. So this is an example. How many cases and controls do I need for this scenario? I have 80% power, 0.05 significance level. Ratio of cases and controls is 1, and I want to detect an odds ratio of 2.2 or greater. Proportion of exposed in the control group is 20. So this is how this looks. So 80% power, that's Z beta, where it will come to 0.84 and then 1.96. These are all things that we know. And then usually you can find an average proportion for an entire pool instead of looking for one. So you just put it in. This is how you pull your proportion. This is formula for pulling proportion for the 2 groups, so that we now have 0.03. This is a formula. And then we calculate our sample size. So there are sample size calculators, so we don't need to cram any of the sample size. So now we've talked about our odds ratio. So odds ratio is the measure of our association used for a case control study, because we cannot measure risk. Unlike what study that you have relative risk, you are just comparing the risk in the risk of the outcome in the exposed and the unexposed. But this one we are calculating, we are looking at the odds. So we're looking at the odds of the exposure in the cases and the odds of having the exposure in the controls. Now, another thing we commonly see is the Cochran-Mantel-Haenszel statistics, commonly just called Mantel-Haenszel. Usually, when you run SPSS, if you have options to select it. So it also helps you calculate, it's like a weighted odds ratio. But many times you see that differences are very minimal if you've been using it. So it's a test using analysis of stratified or matched categorical data. It allows an investigator to test the association between a binary predictor on treatment and the binary outcome. So the limitation, you can only use it for a 2x2 table. So it takes into account stratification. For example, if we are looking at lung cancer and smoking, you might want to look at the subgroups in both, or maybe people that take alcohol or not. That's just an example. So it generates an estimate of an association between an exposure and an outcome after adjusting for or taking into account confounding. So a confounder is a third that is able that distorts the relationship between your two variables of interest. That's between your exposure and your outcomes. For example, I may do a study and I say that I am examining people that have lung cancer, and I find that drinking coffee is associated, that they have higher those that drink coffee have higher odds of having lung cancer compared to those that don't. However, studies have also shown maybe that people that smoke tend to drink coffee more, but smoking itself can independently be associated with lung cancer. So you have a confounder. So it can, you understand, mask the true relationship that you're seeing. So you have to control for confounders, and there are many ways for this. That's one of the reasons why we match. You can match, you can do restrictions. So you are when you are doing restrictions, when you are selecting your control and your cases, you already have strict criteria that you use. So matching is something you do before. So after you have already, when you have done your study, in terms of analysis, you can address confounding, for example, using the Cochrane-Mantel Hensel statistics. You can also address it using your logistic regression. So we stratify the data by two or more levels of the confounding factor. So you create a series of 2x2 tables showing the association between your risk factor and outcome. So for example, I can show it, I have my controls and my cases. I will now separate. I'll do the same thing, or maybe look at those that smoke, don't smoke, look at those that are less than 50, greater than 50, anything. I can look at those that gender, look at males, look at females. So you now repeat the same thing, but at a sub level. So the first thing is to do the standard layout of our exposure and the outcome. So this is how it looks like. This is the mathematical rotation. You have summation A B over N all over B C over N. So AI, BI, C, and D are the numbers of participants in the cells of the 2x2 tables in the I stratum of the confounding variable, and NI represents the number of participants in that same stratum. So this is an example. For example, you are interested in cardiovascular disease as an outcome and obesity. Obesity is our exposure. However, we know that we know that prevalence of cardiovascular disease also increases with age. So age might be a confounder, even obesity. There's weight increase as associated with age. So we can now separate those groups, now run the same table. So we're running it for subsets. So instead of doing a 2x2 table, just looking at presence or absence of cardiovascular disease and obesity in the whole population, we now stratify our population by their age. So we now run the same thing. We run our odds ratio for those that are less than 50. We also run it for those that are 50. So if we calculate it, so we separate our table and the numbers. And if we run this, sorry, I'm looking at time, but I'm sure we'll get the slides if we run this, we find out that for those that are less than 50, sorry, that's odd. So this is it. So, those are less than 50, the odds ratio, this is what we get, 1.48. And then for those that are above 50, we get 1.54. So if we use that data, so you can see that even just by plain stratification, before we apply the equation, you can see that the odds is less, 1.48 in those that are less than 50, 1.54 in those that are. So when we now compare, when we put in a formula from the table, we can see, so it's like a weighted odds ratio. We're taking into consideration all those key variables. We now get 1.52. Like I said, it's just to understand the concept. Our statistical formulas, they will be run when we, so it's just to know that when you are doing a study, you have controls. For your 2x2, it's good to also run your Cochran-Mantel-Haenszel estimates. So you now get 1.52, which is different from what we got from the just plain for those less than 50 and those greater than 50, but it falls in between. But if we see the original table, the unadjusted, sorry, I couldn't go back to that. If we do the original table and we put them together, the unadjusted or crude odds ratio was 1.93. So the CMH method just produces a single summary measure of association that it provides a weighted average or risk ratio or odds ratio. You can also do it for a cohort study across the different strata of the confounding variable. And usually you find out what you get is closer to the stratum specific estimate. So remember when we looked at age, one stratum was less than 50, the other stratum was 50 or above. And you can see it fell just right in the middle of both of them. So this is just for us to know. Many times we don't calculate this. We concentrate, the main measure is the odds ratio, but this can also help when we are thinking of confounders. We can also run logistic regression. It's beyond the scope of our class. But when you also you can run logistic regression with the variables of interest, and that can also be used to deal with confounding. So we talked about matching a lot. Matching is the process of selecting controls so that the controls are similar to cases with regards to certain key characteristics such as age, sex, and race. And we can perform at individual level, that's for everyone, or at group level. So individual level is like match pairs. So for every individual, you're looking for one person, that one person, or two people that look like that person. But usually it's more common to see group matching or frequency matching. So instead of I have a 40-year-old, I'm looking for a 40-year-old, I may just be looking for someone that's between the ages of 40 and 45. So it's more common to see group matching than just individual, like one-on-one matching. So in analyzing case control, one thing I must say, different authors have noted that you don't necessarily have to use math analysis because you matched some of your variables. The only thing you must note when you match, you cannot look for differences from the variable you matched on. It can't be in your analysis. It's like you've taken it out. So it's already because you have already matched them on that. So you've taken them out. You can now put it in logistic regression, or try and find differences in the two groups based on that variable. But in many statisticians say you can still use regular standard analysis. That's how we calculate odds ratio, even when you do a matched case control study. However, in analysis of a matched study design, only discordant pairs are used. So what do we mean by discordant pair? For a concordant pair, the exposure status of the case and the control are the same. So if I have a case, I have someone with lung cancer, control without lung cancer. If they are concordant, that means both of them smoke. If they are discordant, that means one of them smokes, the other does not. It can be either way. It can be the case, it can be the control. So that's what we mean by a discordant pair. So the matched case control study has linked a case to a control based on those variables. And then this is how it looks like. So you can see it now looks different. Before in the columns, we had the case and the controls together as column, and then in the rows, we had exposed or not exposed. But now what you do is you have the cases and then separate them into exposed and non-exposed. And then you also have your controls and you separate them into exposed, not exposed. And then you now count your numbers of the concordant pairs. When you look at exposure, you also look at your concordant pairs. That's A. When you look at A, the number of so you count them in pairs. Number of concordant pairs. When you look at this one is easier when you have like a 1-to-1, but you just look at the number of concordant pairs when you look at exposure, and you look at your concordant pairs when you look at non-exposure. Then now also B now speaks to cases that the internet is back, so we're almost done. So this is just like extra. We've talked about the main thing. So this is how it's done. So this is just an example from a study. So what they do, so in the match case control, all you just do now, you're just going to do the A all over the C. You're going to ignore B and D. So that's just what it looks like. So when we're doing a case control study, design pitfalls.
Dr. Adebayo, are you able to share your slides?
I'm so sorry.
If you're able to share, it's fine. If not, we will just listen to you.
I can share. I just totally, I thought I was back on it because it just came on. I'm so sorry. Let me share.
Okay.
Thank you.
Thank you. We can see your slides now.
Thank you very much. Right. Okay. So we're just going to look. So the A, B, C, D, we're going to ignore A and D. It's just going to be all over C for our odds ratio. So that's just how we're going to ignore the others. So this is just a study that was done. When we share the slide, we can look at, I know we're not supposed to exceed an hour. So the good thing is that all these things can be done with our statistical packages. So it's just, I think the main thing is to know what we need to do so that we can guide the person, analyzing or doing statistics appropriately. We know what we're looking out for when we're doing a case control study. So the design pitfalls to look out for, we should take care to avoid confounding. It's very important. And then controls should be subjects that might have been cases, but they are selected because they do not have the outcome, but they could have been. That's what it's saying. And they are always selected independent of the exposure. Then we should be careful not to overmatch. If you overmatch, you won't find anything. That's just a simple way to put it. And then questions to ask ourselves. In the control is the control group appropriate for the population? Does the study use matching or pairing appropriately to avoid the effects of a confounding variable? And does it use appropriate inclusion and exclusion criteria? So generally, the strategy of approach for data analysis for a case control study, we have to describe the study profile. So that's the number of cases, controls identified, and analysis are normal descriptive. We provide our normal description, baseline characteristics. We do crude odd ratios for the different categories of use and risk factors. And then we do ORs for different categories. So we break it down into subgroup, and we also we control for confounders. So in summary, a case control study is a retrospective study that works backwards. It begins with the health endpoint outcome and then hunting back for possible causes that may have caused that outcome. We have to keep bias in mind. We have to appropriately define our control groups. We should not use just convenient controls, but it should be appropriate so that we get the right conclusion, and then we should avoid confounding. Thank you very much. Over.